Welcome everyone. In this video we will tackle a very classic question when it comes to electric field. Let's say that we have a charged rod, let's say, and it has a charge density of lambda. Now the units of this lambda is coulombs per meter. So this is a linear charge density, which means that since this is homogeneous, since this is constant, the charge is distributed evenly along the length of the rod. And let's say that we define a coordinate system in such a manner. Let's say this is Z, and I'm going to mark the ends of the rod, and this is the x-axis. Okay? Now, let's say that the rod has a total length of 2L. And since, let's say that it is symmetrical with respect to the z-axis, so this is going to be L, and this is going to be negative L, okay? The rod has a total length 2L, L is on the right, and another L is on the left. Now, what we want to find is the electric field due to this rod at a point Z above its midpoint. So this height is Z. And we want to find the electric field here. What is it? Well, if you want, you can pause the video, try it on your own, and when you're ready, continue the video, please. Okay, so now I'm assuming that you want to do it together. You gave it a go, you found it, or you couldn't find it. And in any way, in either case, let's do it together. Now, to carry out the calculation, we want to first think of this rod as if it is made up of infinitesimally small lengths. Let's call them DLs. So we have a DL here, and then we add all of these DLs up, we get the whole rod. Okay? And the reason why we are dealing with this DL is because if we take a little infinitesimal length, we can treat it as a infinitesimal charge. It will have a dq that corresponds to it. And we know the relation between dl and dq. How is it? Well, it is that dq is equal to lambda times dl. Right? So that was one part of it. And the second part is, we will use a symmetry argument. I mean, we see that this shape is symmetrical, and it should be clear to you that, and I don't know if this is a convincing argument, and if it is not, please write it in the comment section and I can give further clarification. But due to symmetry, the effect of the left side is equal to the effect of the right side. Okay? So what I'm trying to say is, we can just calculate the electric field due to the right part and then multiply it with 2 to find the whole electrical field, And that is because, look at this. A DL here will be providing an electric field in this direction. And the symmetrical DL here will provide one in this direction. We can notice that the horizontal components cancel, and we will only have a vertical component. Now, since these two vertical components are the same, the symmetry argument comes in place. We can just calculate the electric field due to the right part and then multiply by 2. Okay? Let's keep that in mind. So I'm just going to write it then. We're going to have E, the electric field. Well, it is going to be, and we already decided on the direction. You might have noticed that, right? E, the electrical field, is going to have a magnitude E, which we will find, and it will be in the z hat direction. Because again, the horizontal components cancel, the vertical components are the only components that are left. So we have the electric field, and we will use Coulomb's law, which says that the electric field due to a point charge is equal to 1 over 4 pi epsilon naught the charge of the point charge, which is going to be dq, over the distance from the charge to the point of interest, which is going to be r squared. So I just defined that, let's use green. I just defined that this distance is r. I hope you realize the significance of the move that we made earlier. Since we chose a dq, a point charge, an infinitesimal charge, we are able to use Coulomb's law because it is stating a fact about point charges. We can't use it for a continuous charge distribution. Well, that is not correct actually. We can use it by putting an integral. We are going to sum up all these dq's, all these little dq's over the entire rod to find the electric field. And since we already talked about the symmetry argument, we can put well, let's not put it right now. Okay, so this is equal. But I mean, this is not a very helpful integration because we don't really know how to relate dq and r, right? I mean, these are constants, but how do we take this integral? And to be able to actually take this integral, we transition from dq to dl. So we have the integral again. Sorry. Hold on. So we have the integral again. And from the symmetry argument, we will add up from 0 to L. And we will multiply by 2 to account for the left side of the rod. And we have 1 over 4 pi epsilon naught. dq is right here. Lambda dl over r squared. Now, what is r squared? R squared is simply going to be, since we have a triangle like this, and it is a right triangle, this part is x. So by the Pythagorean theorem, we can see that r squared is simply x squared plus z squared, right? So we got this. And then for dl, we can write dx because it is simply along the x-axis. It is to the right, let's say. We chose it like that. It is dx. And this is not quite done. I mean, I kind of on purpose made this decision to not say this up to this point because this is a mistake that a lot of people make oftentimes, and especially when you're doing this calculation for the first time maybe. And that is, all the arguments that we made so far, they seem perfectly reasonable. And like, it just seems like if we take this integral, we are done, we're going to get the right answer. However, no. We missed out on a very important factor, very important idea here. And that is, we discussed that the horizontal components cancel, right? If we just leave it like this, we're just like... we're not accounting for it. We're acting as if we're adding up scalars, okay? We're not mentioning that we're only adding up the vertical components. For that, we need to define an angle. And that angle is going to be, with green, it's going to be this angle theta. And it is also the angle here. It is theta as well. So we don't want all of the components. We only want the vertical component, which is sine of theta. Okay? This part is very, very important in this derivation, in this proof. And so if we substitute for sine of theta, we're just looking at the triangle, the opposite side is z. And the hypotenuse is r, which is going to be x squared plus z squared under the square root, so 1 over 2. Which we can just combine here as 3 over 2, right? And I'm going to put the z here as well. Z is here. Cool. So now, only thing that is left is figuring out this integral. But I mean, you might be wondering, how do we exactly do that? And for that, let's first of all take the constants out of the integral sign. So when we do that, let's see. We will have 2z lambda, let's say 2 lambda z. And I'm not simplifying the 2 and the 4 because, 4 pi epsilon naught, they come together all the time. I want to leave them together. That's the only reason. You can simplify it. Okay, you can, of course, simplify them. 4 pi epsilon naught. And then we have the integral from 0 to L dx x squared plus z squared 3 over 2. Now, we want to take this integral, but when you look at it, the derivative of x squared does not appear in the numerator. So we can't just directly take it. However, if we use a trig substitution, we are able to handle this problem. And the substitution that we want to make is that x is equal to z tangent of theta. This is a definition, by the way. This is what we define it to be, right? We take x as z times tangent of theta. We are doing trig substitution. If we take the differential on both sides, it's going to be dx equaling, z is a constant, don't forget, that's why we took it out. Z times, what is the derivative of tangent of theta with respect to theta? It is secant of theta, and then we have d theta, okay? We can just substitute these, that's it. We're going to have let me copy the constants, okay, and now it is not from 0 to L, okay? That was the boundaries for dx. Now we have d theta, so we're just going to have two angles, and we can calculate these angles, but we really don't care. So I will just say theta 1 and theta 2, and you might be surprised that we don't care, but you will understand hopefully in a couple of minutes why we don't need to find theta 1 and theta 2. So now for dx, I'm going to substitute z secant squared theta d theta over. So we're going to have z squared tangent squared theta plus z squared to the power of 3 over 2, right? I just substituted for x. And so in the denominator, if we factor out z squared and if we take it to the power of 3 over 2, we're going to be left with z cubed. And if this step is fast for you, please take a pencil and a paper and do it step by step yourself. And the other part is tangent squared plus 1 under 3 over 2, okay? To the power of 3 over 2. Now, tangent squared plus 1 is just secant squared theta. And if you take it to the power of 3 over 2, the 2's will simplify, so you will have secant cubed of theta. Secant cubed of theta, right? And so, I'm taking this step very quickly, but anyways. So let's simplify these z's. And if we simplify the secant, we will just have a secant which will turn out to be cosine because it is the reciprocal of cosine. So we will have, let me write it here, 2 lambda over 4 pi epsilon naught. I take the z out, z, the boundaries that we don't care about, and then cosine theta d theta. Now the integral of cosine theta is simply sine of theta because the derivative of sine is the cosine. So I will substitute this. 4 pi epsilon naught z sine of theta. And this is the part that we don't care about the angles. Because, we would write the boundaries like this, right? And then we would need to evaluate these. But instead, I propose that we resubstitute. So I want to now write something in terms of x and z for sine of theta. And we can do it. Because since we made this definition, let me draw the triangle here. We have theta, and the tangent is x over z, so opposite is x, and adjacent is z. Or at least that's how we can choose it, right? You could put like constants here, but it doesn't matter when you take the ratio. And so the hypotenuse is going to be x squared plus z squared. It is basically, it's basically this triangle that we have, okay? And so what is the sign then? It is x over x squared, it's x over the square root of x squared plus z squared. So I write it, x over x squared plus z squared under the square root. And now, as you can see, we are back with x, which means we are back with the original boundaries of L and 0. Now, I think it is quite evident that when you plug in 0, this goes to 0, so we don't even need to worry about the lower boundary. So we just substitute the upper boundary, which gives us, well, let's write it in a nice way. So it is going to be 1 over 4 pi epsilon naught 2 lambda L over, let's see, over L squared plus Z squared under the square root. And this is the magnitude of the electric field at a point Z above the midpoint of our rod, of our charged rod. And don't forget, due to, oh, hold on a second. I also forgot the, excuse me, I got too excited. We have the Z here, remember? We have Z. So its Z is going to be here. Yeah. Anyways. So yeah, what was I saying? As you can see, we found the formula, and don't forget that it is in the positive Z direction. It is upwards due to symmetry. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. If you like the content, please subscribe, and see you in the next video. Until then, take care.